Hello, today we'll continue with lattices, which play an important role in many areas of mathematics and also in more applied areas like cryptography. We'll prove the following. So first, remember that a lattice is just a discrete subgroup of Rn, and we'll prove that every lattice has a basis, so it's of the form CB1 plus and so on up to CBK. Where the BIs are linearly independent. Note that the converse also holds, so for the converse, that's relatively easy, so it's certainly a subgroup. So for discreteness, it's easy to check that we only have to check it around 0, and then we can complete the basis if necessary, and we consider the set of AI BI, where the modulus of the AIs is less than 1, and then we get that U intersection with this CB1 and so on up to CBN. Let's say now, let's consider a full rank lattice. So as I said, if necessary, we can complete the basis, and this is just 0. So this gives us discreteness. Okay, but now let's prove the other direction. So first, one can check that every lattice is closed in Rn. That needs a little work, but it's not that hard. So once we have that it's closed, we'll consider, so take a maximal set of linearly independent vectors, let's say C1 up to CK in the lattice, and what we want to prove is that this subgroup or this sublattice has finite index in lambda. So let's maybe call it lambda prime. Okay, so let's prove the claim first. So how do we do this? So let's consider the set, let's call it maybe phi, which is the set of AI CI with AI less than or equal to 1. Okay, that set is certainly compact. And phi intersection with lambda is now compact and discrete. So compactness follows from compactness of phi and the fact that lambda is closed in Rn. And this means that this intersection is actually finite. So this now implies that lambda, so the index, is also finite. That's relatively straightforward. So we have finitely many lattice points in here, and this tells us that the index is finite. And now we are almost done. So this means that there exists, let's say, an L such that L times lambda is in lambda prime for all lambda in capital lambda. And we know what lambda prime is, so that's of this form. But that's now a free module over the integers, so the integers are a principal ideal domain, which means that L, lambda, and therefore also lambda is a free module of rank less than or equal to k over the integers. And since lambda prime is a subset of lambda, it has actually rank equal to k. Okay, now that's what we wanted to prove. And note that actually, so here we have these ci's. They don't have to be equal to these bi's, but so the bi's from here, but we get the bi's, so that's fine, and we know that we have a basis for our lattice. Okay, that's what I wanted to cover in that video. I'm not sure yet what the next video will be about, but we'll see. So thanks for watching, have a good day, bye.